We now determine the points of inflection of the graph of the function f of x equals 8x cubed minus 6x squared minus 10x plus 1. So the points of inflection are the points of the function where it changes concavity. That is, if it changes from concave up to concave down, or if it changes from concave down to concave up, we see that it has points of inflection. So let's see how to determine the points of inflection. To determine the points of inflection, we have to set up the second derivative equals 0, or the second derivative is undefined. So we obtain the points of inflection usually when the second derivative is 0 or when it is undefined. So first, let's find out the second derivative of the function f of x. Let's differentiate this function first. So it is basically the first derivative of f of x, which is f prime of x, and this equals, we differentiate each terms on the right side. That is, the derivative of 8x cube is 8 times of the derivative of x cube, which is 3x squared, and then the derivative of 6x squared is negative 6 times the derivative of x squared, which is 2x, and the derivative of negative 10x is negative 10 times the derivative of x, which is 1, and the derivative of 1 is a constant, so it is 0. So let's simplify this. This is basically the first derivative of the function, which is f prime of x, and this equals 24x squared minus 12x minus 10. Now let's find the second derivative by finding the derivative of this f prime of x. So we get f double prime of x, and this equals 24 times of the derivative of x squared is 2x using the power rule, minus 12 times of derivative of x is 1. So we get 24 times 2 is 48x, minus 12 times 1 is 12. So this is basically the second derivative of the function f of x. Now let's set them up equal to 0, that is the second derivative equals 0, and solve for x. So replace second derivative by 0, we get 0 equals 48x minus 12, and this gives 48x equals 12. So we solve for x as equal to 12 over 48, and this equals 1 fourth. So x is basically 1 fourth, or in terms of decimal, this is 0.25. And we need to verify if this is the points of inflection by preparing a sign chart for the second derivative of the function. So let's prepare a sign chart for the second derivative. So we put this number line, and also this 1 fourth. This is x equal to 1 fourth. And let's consider the second derivative, that is f double prime of x, and this equals 48x minus 12. I copy this. So basically we are preparing the sign chart for a second derivative of x. Considering this point x equal to 1 by 4, we take some any random value to the left of x. So I'm going to take x equal to 0 and plug it into second derivative. So therefore it becomes f double prime of 0, and this equals 48 times 0 minus 12, which is basically 0 minus 12 is negative, so it is less than 0. So we see that to the left of x equal to 1 by 4, the second derivative is negative. Now let's check on the right of x equal to 1 by 4 by plugging in any random point to the right of x equal to 1 by 4. I'm going to plug in x equal to 1. So therefore it becomes f double prime of 1 equals 48 times 1 minus 12, and this is basically 48 minus 12, which is 36, and this is greater than 0. So to the right of x equal to 1 by 4, it is positive. And this means we can say that according to the second derivative and the concavity definition, whenever the second derivative is negative, it is concave down. That is, the graph will look something like this. And whenever it is positive, it is concave up. So the graph will look something like this. That is, it is opening upwards. And so we see that in this interval, that is from negative infinity to positive 1 by 4, we see that it is concave down, and in the interval from 1 by 4 to positive infinity, it is concave up. And clearly at x equal to 1 by 4, it has a points of inflection, because we see that the graph of the function changes its concavity. That is, it changes from concave down to concave up. So definitely x equal to 1 by 4 is a point of inflection. And so we can give the xy pair of the points of inflection. For that, we need to determine the y. So we can plug in x equal to 1 by 4 into the original function to determine the corresponding y value. So let me copy the f of x, which is f of x equals 8x cube minus 6x squared minus 10x plus 1, and we have to plug in this x equal to 1 by 4 into the function, so that we get y. So it becomes f of 1 by 4, and this equals 8 times of 1 by 4 quantity cube minus 6 times of 1 by 4 quantity square minus 10 times of 1 by 4 plus 1. And so this equals 8 times of 1 by 4 quantity cube is 1 by 64, and minus 6 times of 1 by 4 quantity square is 1 by 16, minus 10 times of 1 by 4 plus 1. So we have the common denominator of 64, and this means this numerator we just keep it as it is, and then this numerator we have to multiply by 4, because here we have the denominator 16. So to make it as a common denominator, we should multiply and divide by 4. So therefore 6 times 4 is 24, and then this numerator we should multiply by 16, because the denominator is 14. So to make it a common denominator, we should multiply by 16. So 10 times 16 is negative 160, and then for this we have to multiply by 16, because here we have the denominator 1. So this numerator has to be multiplied by 116, that is 60. We have to multiply by 64, and so this simplifies to negative 112. This is 2 divided by 64, and this is equivalent to negative 1.75. So this is the y value of the inflection point. Now let's give the inflection point as an ordered pair, that is points of inflection as an ordered pair x comma y, and this equals we already found the x, which is 1 by 4. So we write down 1 by 4 comma negative 1.75, or we could also write down 1 by 4 in terms of decimal, which is 0.25 comma negative 1.75. So this is the points of inflection. We now write the concave upward as well as the concave downward interval using the sign chart we prepared for the second derivative of the function. So here we have the second derivative of the we have the sign chart of the second derivative. So we have already determined that in the interval negative infinity to 1 by 4, it is concave down. So I write down negative infinity to 1 by 4, or we could also write down this in decimal notation, that is negative infinity to 0.25. It is concave downward, and in this interval, that is 1/4 to infinity, it is concave upward. See, we write down 1/4 to infinity, or in terms of decimal it is 0.25 to infinity, it is concave upward. So these are the intervals of concave upward and concave downward.